Good evening everyone. My name is Devlina Maiti. I'm a research scholar in the Department of Mathematics IIT Kharagpur and also NPTEL TA for the course Basic Real Analysis, and the course instructor is Professor I.K. Rana. So this is the 11th problem solving session, and in this session we are going to discuss about pointwise convergence and uniform convergence of sequence of functions. Okay, so let's start this series. One second, I think this is not working. So let A be a subset of R and suppose that for each n, belongs to the natural number, there is a function fn from A to R. Okay, then we say that this fn is a sequence of function. So we already know about sequence of real numbers. Now we are taking sequence of functions. So each of this term is a function, not a real number, it is a function. So for each x, belongs to A, this fn x, this is a sequence of real number. Right? Because this sequence is what? The first term is f1x, second is f2x, then f3x, and so on. So this is for each x, this fnx is a sequence of real number, and this fn is a sequence of functions. Now for some x, this sequence may converge, and for some x belongs to A, this sequence may not converge. Right? Now we'll define pointwise convergence of this sequence of function. So take a subset D of R, and for each n, let this fn from D to R be a function. Okay, then the sequence of function is said to converge pointwise, or is said to be pointwise convergent. On D to a function f if for each x x in D, the sequence fnx converges to fx, right? If for each x fnx, this sequence of real numbers fnx converges to fx, then we say that fn converges to f pointwise, right? Now what is this f? So for each fnx, so for x belongs to D, fnx converges to fx, right? Or now we want to find what is fx. Now this sequence for each x, this sequence fnx, this convergent, this is a convergent sequence, right? So for each x, this fnx converges to some kx, right? For each x. Now if we define fx to be kx for x, for all x belongs to D, then this is our function f. So this implies fnx converges to fx, right? This sequence fnx, this is our function f. So this is convergent. Since this real number sequence is convergent, so for each x we are getting some kx. Fnx, since fnx is convergent, we are getting some kx. Now we are defining f to be that kx. For each x, that number we are finding, this kx, we are defining for each x to be this kx. Then fnx converges to this fx. Alright. Now we are going to see some problems. So for each n, define fnx, which is a function from R to R, and it is defined by fnx equal to x to the power n, where x belongs to R. Then we have to find that where it is pointwise convergent and to which function. Okay. Now we see that for each x belongs to this open -1 to 1, what is this sequence of fnx is what? Fnx is x and then x square, x cube, and so on. Now since mod x is less than 1, then this sequence goes to 0 as n tends to infinity, right? This sequence of numbers, this fnx, this means fnx goes to 0 as n tends to infinity. So for each x, it is going to be 0. So what is the pointwise limit? It is the 0 function, right? So this means, okay, it is for this open -1 to 1. Now what about x equals to 1? So when x equal to 1, this series fnx becomes this constant 1. So this is also convergent, right? So then our fnx converges to 1, right? And for x greater than 1 or less than -1, or if we say x is -1, then fnx will be this series. this alternating series, -1 +1 -1, oscillating series. So this is not convergent. This is not convergent. And also if we take x greater than 1 or x to be less than -1, then also x to the power n, this sequence is not convergent. Right? So only in this neighborhood, this -1 to close 1, this sequence for each x belongs to this portion, fnx is convergent. Fnx is convergent, right? And it converges to what function? It converges to the function this 0 when x belongs to open -1 to 1. We have already seen that in open -1 to 1, fnx converges to 0. And when x equals to 1, it is 1. Right? So fnx, so therefore the sequence fn is pointwise convergent on -1 to closed 1, and the pointwise limit is, and this f function, and the function f is its pointwise is the limit function. Okay. So this function fnx converges pointwise to this function f, this f, in this section -1 to closed 1. Okay, let's see another example. So for each n, we are defining now fnx equals to x by n, where x belongs to R. Now, is this sequence of function convergent, pointwise convergent? And if it is pointwise convergent, then what is the limit? Right, where x belongs to R. Now, how does these functions look like? Now, in example 1, now how does this sequence look like? So, if we only see in -1 to 1, so the first function is our x, right? So it is this line. This line. So it is our f1. Now the second one is x square. So second one is this parabola, right? So it is f2. And the third one is x cube. So it will be some lower than this f2, this f3, and it will be negative here. So this is f3, right? Now like this, it is going to be 0. Not 0, the limit function will be, the limit function is 0 when x belongs to -1 to 1, and 1 when x is 1. so it is a discontinuous function, right? But all of this fnx, they are continuous function, but it is converging pointwise to a discontinuous function, right? Now in example 2, so the first function is our x, right? So it is, this is f1, and the second one is x by 2, so it will also be a line, so this is f2, and then this will be f3 and so on, right? Clearly if we see, look at the image, you can clearly conclude that this is, when n goes to infinity, this sequence of function goes to be 0, right? They are getting closer to the x-axis. Okay, now we'll prove that. So fnx is our x by n, right? Now for each x belongs to, now for x belongs to R, what is fnx? The sequence is, since our x is fixed now, so it is, first is x and then x by 2, x by 3 and so on, right? But since our x is fixed and this is, and n is increasing, so fnx goes to 0 as n tends to infinity, right? So for each x belongs to R, fnx, the sequence of real number, goes to 0. So the pointwise limit is what? So this is the 0 function. Fx is 0 for all x belongs to R, right? So therefore fn converges pointwise to the limit function fx is equal to 0 for all x belongs to R, right? So fnx converges pointwise to this function. This is the limit function, which is 0 function. Okay, so this was an easy one. Let's go to the next one. So in 3, D is this set, all those x belongs to R such that x is greater or equals to 0, that is 0 infinity, and fn is defined to be, fn is from D to R, which is defined by fnx equal to nx by 1 plus n square x square, where x greater or equals to 0. Now we'll see its pointwise converges to what function? Okay. Now for x equal to 0, this sequence fnx is 0 function, this is 0 sequence, right? So then fnx converges to 0 when x equal to 0. Now for x not equals to 0, limit n goes to infinity, fnx is what? This x equal to one plus n square x square which is equal to, if we divide it by n square, then we'll have x by n right. So it is going to be, when n goes to infinity, it is going to be 0. So for every point, this function is not n square x square, it is also nx. Okay, this is 1 plus nx. So then it is going to be, if we divide it by n, then we will have x by this one. So now we are getting, it is going to be 1, right? So when x equal to 0, fnx converges to 0, and when x is non-zero, then fnx converges to 1. So the limit function, so therefore the sequence fn is pointwise convergent on D to the function, and the pointwise limit is, fx is what? Fx is 0 when x is 0 and 1 when x is greater than 0. X is non-zero means x is greater than 0, because our D was what? X greater equals to 0. So this sequence converges pointwise on D to this function. Okay, so let's see another example. Okay, so it is 4. So let fnx be sine of nx by n when x belongs to R. Right. Now what is this? It's pointwise convergent function, pointwise convergent limit function. So in this function, this sine function is bounded, right? Sine of nx is a bounded function, right? So sine nx by n, it is bounded by 1 by n, right? And greater equals to 0. So by the sandwich theorem, limit n tends to infinity, sine nx by n is going to be 0, right? So this implies limit n goes to infinity, fnx is 0 for each x belongs to R, right? So this limit is not depending upon x. For each x, this is going to be 0. So this implies, so fn is pointwise convergent on R to the function f defined by fx equals to 0 for all x belongs to R, right? So it is converging to the 0 function, this sequence, pointwise convergent to the 0 function. Okay. So let's take another one. So this is given by, for each n, fn x is given by x square e to the power minus nx when x greater equals to 0. Okay. So we have to find is pointwise limit, right? So when n goes to infinity, what is fn x? Now we see that e to the power nx equals to what? The power series of e to the power x is 1 plus x square by 2 and like that, right? So this implies this is n square x square by 2 plus and so on. So this is clearly strictly greater than n square x square by 2, this term, right? This is 1 plus this term plus and something, right? So this is clearly greater than n square x square by 2. So this implies x square e to the power minus nx is less than 2 by n square, right? So this implies 0 less equals to this x square e to the power minus x is our fn x, which is strictly less than 2 by n square. 2 by n square. So by sandwich theorem, limit n tends to infinity, fn x is going to be 0, right? So the limit function here is also the 0 function. Okay, so therefore the sequence fn is pointwise convergent on 0 infinity to the function f defined by, it is the 0 function for all x belongs to 0 infinity, right? So this function is pointwise this sequence of function is pointwise convergent in this domain, and it is converging to the 0 function, right? Okay, now let fn converges to f pointwise, right? Then and let this x dash belongs to d. D means here this fn are defined in d toward. Okay, so if x dash belongs to d and we choose some epsilon greater than 0. Now since it is convergence pointwise, so at each point it is going to be, so for x dash, fn of x dash is converges to fx, right? This is a sequence of real number which converges to fx, right? Now for limit, we know that if xn converges to x, if and only if given any epsilon greater than 0, there exists some natural number n belongs to this natural number set such that mod of xn minus x is less than epsilon for all n greater equals to this capital N. Right? This is the epsilon definition of limit. Right? Now here we have fnx converges to fx. So if since epsilon is given, so this means there exists some k dash in n such that mod of fn of x dash minus f of x dash, this is x dash, is less than epsilon for all n greater equals to this k dash. Right? Now similarly, if we take a different point other than this x dash, so let's take x double dash belongs to this D and epsilon is given, then there exists some k double dash belongs to n such that this happens less than epsilon for all n greater equals to k double dash. This k dash and k double dash may be different, may be equal, right? That we don't know. But what we are seeing is that for each x dash, we are getting some k dash such that this happens, right? For each x dash, we are getting some k depending upon that x such that this equation, this holds, right? Now our aim is that does there exist, for a given epsilon, does there exist a uniform k dash, uniform k for which this happens for all the x, right? So what I am saying is that for each x belongs to D, there exists some kx, k depending upon this x, and epsilon belongs to this natural number such that fnx minus fx is less than epsilon for all n greater equals to this k epsilon x. Right? Now, is it possible for given epsilon greater than 1, there exists a natural number k belongs to n such that mod of fnx minus fx is less than epsilon for all n greater equals to k and for all x belongs to D. Right? Now we are saying that does there exist an uniform k? This means this k is working here for all the x belongs to D. Here our k depends upon x. For if we change x, we are getting different k. Now the question is, can there be a k, uniform k, which works for all the x in D? Right? And for this issue, they came up with the uniform convergence. So in uniform convergence, we will see that for each epsilon greater than 0, there should be an uniform k which works for all the x. So uniform convergence of sequence of function. Right. So what is uniform convergence? So let first D subset of R. And for each n belongs to n, let this Fn, this sequence of function, this is be a function. Right? Now the sequence fn is said to be uniformly convergent on D to a function f if given epsilon greater than 0 there exists a natural number, there exists k belongs to n. This is depending only upon epsilon, but not on x. Does not depend on the point, such that for all x belongs to D, mod of fnx minus fx is less than epsilon for all n greater or equals to k. Right? So this is same like uniform continuous. So fn is said to converge uniformly this sequence of function to a function f if given epsilon greater than 0 there exists a natural number k which depends only upon epsilon, such that for all x this happens. So that's why it is uniform. It does not depend upon the points. Right? And then we say that, then we write fn converges to f uniformly or limit n tends to infinity fn equals to f uniformly. When fn converges to f uniformly, we write in this form. Okay, let's see some examples. So let's take the first example we have chosen for pointwise convergent. So which was fnx equals to x to the power n when x belongs to open minus 1 to closed 1. Right? Then we have seen that the limit function f is fx equal to 0 when x belongs to open minus 1 to 1, and when x equals to 1 it is 1. Right? Now the question is, does fn converges to f uniformly? So fn converges to f pointwise. Right? Pointwise. Now the question is, does fn converges to f uniformly? This is done. This is our question. Okay, so let's take a point C between 0 to 1. Okay. So for uniform convergence, what we have to show? We have to show that for a given epsilon, this occurs. Right? For all x belongs to D. Right? Now in 0 to 1, we have chosen this C, and then fnc minus fc, since c belongs to 0 to 1, fc is 0, so it is basically c to the power n minus 0, which is c power n. Now choose some epsilon greater than 0 and less than 1. Okay, then mod of fnc minus fc will be less than epsilon whenever this c to the power n is less than epsilon. So whenever c power n is less than epsilon, right? Now c power n is less than epsilon means what? This means n log c is less than log of epsilon, and since c and epsilon both are less than 1, these are negative terms, so in positive they will be in greater or equals to, we'll write it as 1 by epsilon and 1 by c, right? So you see that whenever n is bigger than this number, then this occurs, right? Now since it is not a natural number, so we will make it natural by choose k to be box of log 1 by epsilon by log 1 by c plus 1. Then k is a natural number and k is bigger than this number, right? Bigger than this one. So this implies so k belongs to this, and mod of fnc minus fc is less than epsilon for all n greater or equals to this k, right? Because this happens when n is greater or equals to this number. This happens when n is greater or equals to this number. Now what we choose to be k is bigger than this number, so this occurs when n is greater or equals to k. And since our c is arbitrary in 0, 1, okay, now we see that this k, this number k depends upon the point, right? Because it depends upon this c. C is a point in 0, 1. So this k we are getting depends upon the point and epsilon also. So this convergence is not uniform, right? So this means this k depends upon epsilon as well as c, the point. Now we have seen this in 0 to 1, right? So therefore also here we see that when c goes to 1, when as c goes to 1, this k is going to be infinity, right? So therefore it is not uniformly convergent on 0, 1. So therefore Fn is not uniformly convergent on open 0, 1, because the number k here is depending upon epsilon as well as c, the point. So that's why it is not uniformly convergent on 0, 1. Now can we find a subinterval of 0, 1 where it is uniformly convergent? So for this, let take A belongs to R such that 0 less than A less than 1, right? So we are not choosing the whole 0 1, we are taking a point. This is 0 1, we are taking a point somewhere between 0 and 1, right? Now in this closed interval 0a, so our value of k was what? This one, the greatest. So k is log of 1 by epsilon by log of 1 by c plus 1, right? Now this is less equals to log of 1 by epsilon by log of 1 by a plus 1, right? In this interval k is less equals to this number, right? So the greatest value of k in this subinterval is going to be this one, right? So the greatest value of k in this section when x is in this portion is log 1 by epsilon by log of 1 by a plus 1, right? And this number, we see that this is epsilon. This number is not depending upon the points between 0 to a. There are points c, but this k is not depending upon. Now if we choose this to be k dash, then we'll see that then for all x belongs to this portion 0 to a, mod fnx minus fx is less than epsilon for all n greater or equals to this k dash, right? Right. Now this k dash is not depending upon the points between 0 to a. This is depending upon a fixed point a. So this means fn converges to f uniformly on 0 to a, on closed interval 0 to a, where a is fixed between 0 to 1, right? A is fixed between 0 to 1. But on the whole open interval 0 to 1, this is not convergent, right? Because it is not defined at the point 1. It goes to infinity as c goes to 1. That's why. Okay. So this function converges uniformly on a closed interval 0 to a, where a is less than 1, right? Where 0 less than a less than 1. Alright. So let's go to the next problem. So the problem we have taken x by n when x is greater than 0 or 0 infinity, right? And we have seen that this function converges pointwise, if n converges to pointwise to f where fx is 0 for all x greater or equals to 0, right? The 0 function is this function's limit function. The sequences, this fn converges pointwise to the limit function, the 0 function, right? Now does it converges to f uniformly? Now, this is the question. Converges to f uniformly. and if not, where it is uniformly convergent. On this, if it is not uniformly convergent in the whole domain 0 to infinity, then can we find a subportion of this interval where it is uniformly convergent? We'll check this. So for all x greater equals to 0, fnx minus fx is what? This is fx is 0 and fnx is x by n, so it is x by n, right? So we have to choose epsilon greater than 0, right? And we have to find a k for which this fnx minus fx modulus of is less than epsilon whenever n is greater equals to that k, right? So fnx minus fx less than epsilon whenever x by n is less than epsilon, right? So this implies n is greater than x by epsilon. Whenever n is greater than x by epsilon, this holds, right? So if we choose k to be, this is n, if we choose n dash to be, x by epsilon is not a natural number, so if we choose n dash to be this, now this belongs to n, and since this number is also greater than x by epsilon, this will also be true. So fnx minus fx is less than epsilon for all n greater equals to this n dash, right? This n dash. Now we clearly see that here also this n dash depends upon the point x, right? There is x here, x is the point, so this number n dash also depend upon x. So this n dash depends on epsilon as well as the point x, right? So that's why this convergence will not be uniform convergence. So therefore fn, the sequence fn is not uniformly convergent on 0 infinity, right? It is not uniformly convergent on this domain. Now is there an subdomain of this where it is uniformly convergent? Now if we bound it, so let's take a belongs to R such that a is greater than 0, not 0, a is greater than 0. So we have 0 infinity. Now we are bounding it somewhere between 0 and infinity. This is a, which is strictly greater than 0, right? Now we'll consider this on this closed 0 to a, not 0 infinity. We are now check uniform convergence on this closed 0 to a. Now in this closed region, closed interval 0 to a, what we have fnx minus fx, which is x by n, right? Now the largest value of this x by n is what? This is a by n, right? So the largest, the greatest or largest greatest value of this fnx minus fx in 0 to a is a by n, right? So if a by n is less than epsilon, then automatically fnx minus fx is less than, which is actually equal to x by n, is less than f by n, and which is less than epsilon n, right? For all x belongs to 0 to a, right? So if this happens, this a by n is less than epsilon, then fnx minus x is less than epsilon for all x belongs to 0 to a, and this means what? This means n is greater than epsilon by a, right? Now you see that this n is not depending upon x, right? So if we choose n dash to be epsilon by a, box of epsilon by a plus a, now it is clearly greater than epsilon by a. So this implies fnx minus fx is less than epsilon. This will also be true, less than epsilon for all x belongs to 0 to a and for all n greater equals to this n dash, right? So whenever n is greater than this number, this is true, and this n dash does not depend upon the point x, it is only depending upon epsilon. So that's why this convergence here in this domain is closed 0 to a, it is uniformly convergent. So therefore fn converges to f uniformly on this closed 0 to a, where a is some point greater than 0, right? Okay, so we have found that this is not uniformly convergent on the whole domain 0 to infinity, but it is uniformly convergent on this 0 to a. Okay, let's go to the next problem. So take fnx to be x into e to the power minus nx, right, where x is greater or equals to 0. We have already seen that in pointwise convergent. So this fnx converges, fn converges to a pointwise, where this function f is the 0 function, 0 for all x greater or equals to 0. Now we'll check for the uniform convergence, right? So for all x greater or equals to 0, mod of fnx minus fx equals to what? This is x e to the power minus nx, because fx is 0. Now e to the power nx is, the series is like that. So it is strictly greater than nx when x is greater or equals to 0. So this implies in x into e to the power minus nx is strictly less than 1 by n, right? So mod of fnx minus fx is strictly less than 1 by x for all x greater than 0. Now this is less than 1 by, so when n tends to infinity it is going to be 0, or for in case of epsilon delta, so if we choose epsilon greater than 0, then we'll choose this k to be box of 1 by epsilon plus 1, right? Then k belongs to n and mod of fnx minus fx, which is less than n, will be less than epsilon for all n greater or equals to 1 by epsilon, right? So that's why we have chosen k to be one box of 1 by epsilon plus 1. So then k belongs to n and mod of fnx minus fx is less than epsilon for all n greater or equals to this k, right? Because now k is greater than 1 by epsilon. So this is true for all, and it is true for all x greater or equals to 0, right? And k does not depend upon x. So this implies fn converges to f uniformly. So fn converges to f uniformly, right? So this function converges to f. So fn converges to f uniformly, right? Now we'll see a criteria by which we can tell that if the convergence is uniform or not, which is called the Cauchy criteria. So what is Cauchy criteria? A necessary and sufficient condition for uniform convergence of the sequence fn on D, a subset of R, is that for a given epsilon greater than 0, there exists a natural number k belongs to n such that for all x belongs to D, mod of fmx minus fnx is less than epsilon for all mn greater or equals to this k. Right? So this is the Cauchy criteria. This is a if and only condition. This is necessary sufficient condition for uniform convergence. So fn converges uniformly if for a given epsilon greater than 0, for all x belongs to D, we will find a k for which this happens, right? Now we'll see a problem and we'll solve this by this Cauchy criteria. So let R1, R2, R3 be an enumeration of the rational numbers Q in 0, 1, right? That is the set of all rationals in 0, 1. So since this set is countable, we are enumerating this, and this R1, R2, R3 to infinity, it is an enumeration of this set. Okay. And a sequence of functions Fn is defined on 0, 1 by Fnx will be 0 if x is R1 to Rn and 1 otherwise. This means 1 when x belongs to 0, 1 minus this R1, R2 to Rn, right? So for finite, so if this is n, this n means up to n it is 0 in these discrete points, and otherwise it is 1, right? So it is 1 on the whole 0 to 1 except for these points. At this point these are zeros, right? Clear? This is our function, sequence of function. Now I have to show that this function, sequence of function Fn is not uniformly convergent. Right? We have to show that this is not uniformly convergent. So by Cauchy criteria, this is not uniformly convergent means what? So here we said that for a given epsilon, we have to find a k. There exists some k, right? Now here, this means for every epsilon, there exists some epsilon, given any epsilon, so this means there exists some epsilon for which for all k this will not be true. Means for all k, since there exists a k, this means so for all k there should be an x naught in D for which this will not happen, right? So first we'll take epsilon to be half, right? Now we'll see that it is sufficient to show the negation of this Cauchy criteria is what? So it will be sufficient to establish that for all k, now there exists some k, so here it will be for all k. So for all k in n, and mn was for every mn, so here it will be there exists some mn. So there exists mn belongs to n such that mn will be greater or equals to k and this equation will not be true. So this means for all x here it was for all x belongs to D, so there exists some x naught. So fn of x naught minus fm of x naught is not less than half, that is our epsilon, for some x naught in D, that is 0 1, right? That this we have to show. So we have already chosen some epsilon. Now for all k we have to find this m and n, right? Now you see that for all k belongs to n, what is this fkx? Fkx is 0 if x belongs to this set R1 to Rk, and otherwise it is 1. This means if x belongs to 0 1 minus this R1 R2 Rk, then it is 0, right? This is fk function. Now for every k belongs to n, there exists a point r, some Rn plus 1. Rn plus 1 is a rational number, right? So Rn plus 1 belongs to 0 1 such that what happens? This fk of Rk plus 1 minus f of k plus 1 of Rk plus 1. What is this number? Now fk of Rk plus 1 is what? This is our fk function, right? Now Rk plus 1 belongs to here. It does not belongs to here, it belongs to here. So its value is 1. Now f of k plus 1, Rk plus 1. Now for f k plus 1, Rk will be in this set, right? In this set. So then it will be 0. So this value is actually 1. So for every k we are finding that we have found a point. This is our x naught, this x naught. We have found a point for which this difference, and this here we have to find this mn. So here mn is what? K and k plus 1. For k and k plus 1, this value is 1, not less than, which is not less than half, right? So we have proved the negation of Cauchy criteria. So this implies there exists therefore no natural number k can be found such that this happens. So this implies, so we have proved the negation of Cauchy criteria. So by Cauchy criteria, fn, the sequence of function fn is not uniformly convergent. It's not uniformly convergent on this 0 1, right? So we have proved this by Cauchy criteria. Okay. So next we will see a theorem. So this theorem also is a condition for uniform convergence. Okay. So let D is a subset of R and fn is a sequence of function. Fn be a sequence of functions pointwise convergent to a function f on this D. Now let Mn equals to supremum of this x belongs to D mod of fnx minus fx. So what we are seeing is that this is less than some number, right? Now we are taking the supremum of this difference in the whole domain. We are taking supremum of modulus of fnx minus fx in the whole domain. Then we'll say that fn converges to f uniformly if and only if limit n tends to infinity mn is 0. This is an if and only if condition. If limit of mn goes to 0, then fn converges to f uniformly. Okay. So okay, for time being I am not proving this theorem. You can find the proof of this theorem in any book of real analysis. Okay. Now we will use this theorem to prove some problems. Right? Okay. So let's take some problems. Right? So prove this. See the proof in any real analysis book. Right? Now use this theorem. This is a very important theorem. So take fnx to be 1 minus x to the power n by n, where x belongs to 0 to 1. Right? Then show that fn converges to f uniformly on 0 1. Right? This we have to prove, and we will use this theorem. Since this is an if and only if condition we are getting here. Right? So first we have to find the pointwise limit of this sequence. Right? So first we have to find limit n tends to infinity fnx. So for 0 less equals to x less than 1, limit n tends to infinity fnx is what? So this is going to be 0. This is actually n tends to infinity 1 minus x to the power n by n. For x equals to 0, this is also 0, and x equals to 1, this is also 0. So this is going to be 0 for all x in between 0 to 1. So fn converges, because for this theorem first we have to find out the pointwise convergent function of this sequence fn. Right? Then we have to find this mn. So fn converges to f where f is 0 function for all x belongs to 0 1 pointwise. Right? So fn converges to f pointwise. Now we'll find out this mn. Now what is mn? So mn was supremum of this difference. Right? So mn is supremum. Here the domain is 0 1, and it is fnx minus fx. So fx is 0, so it is supremum of fnx is mod x to the power n by n, right? Now we are taking the supremum, so it is going to be 1 by n, supremum over x, where x lies between 0 to 1. So the supremum value is 1 by n. So since mn is 1 by n, limit n tends to infinity, mn is 0, right? So this follows, this mn, limit n tends to infinity, mn is 0. So by this theorem, fn converges to f uniformly on 0, 1, right? So we have used this theorem to prove that fn converges to f uniformly on this closed interval 0, 1. Okay, let's go to the next problem. So next problem is fnx equals to nx by 1 plus n square x square, where 0 less equals to x less equals to 1. Now you have to show that the sequence fn is not uniformly convergent. Convergent in 0, 1, right? So again we will use this theorem since it was a necessary sufficient condition. So first we have to find out the pointwise limit, right? Now for x equal to 0, this sequence fnx is the 0 sequence, right? This is what? The first term is also 0. We are just putting 0 in fnx, x equals to 0. So this is the 0 sequence. So this means fnx goes to 0 for x equals to 0. Now for 0 strictly less than x less equals to 1, limit n tends to infinity, fnx equals to what? This is equals to n tends to infinity nx by 1 plus n square x square, which is equals to, this is x by n 1 by n square plus x square, right? Since x is not 0, so this is going to be 0, right? So if nx goes to 0, also for 0 to 1, so the limit function is the 0 function. So fx equal to 0 for all x belongs to this 0, 1 is the pointwise limit of the sequence fn, right? Now we'll show that it is not uniformly convergent. Okay. Now for x greater than 0, we know that the arithmetic mean of nx and 1 by nx, that is this number, right? This is the arithmetic mean of nx and 1 by nx. So this is equals to the geometric mean of these two numbers. So which is equal to 1 by nx into nx, right? And the equality will hold, hold when nx equals to 1. This means x equals to 1 by n, right? When nx equals to 1, then equality holds. So when x equals to 1 by n, the equality holds in this case. Now this is same as saying that 1 plus n square x square by 2 nx is greater or equals to 1, and the equality, this line is same, these two line is same, and the equality holds for x equals to 1 by n. And this line is same as, so our function was what? Nx by 1 plus n square x square. So this means nx by 1 plus n square x square, this term is less equals to 1 by 2, and the equality holds for x equals to 1 by n, right? Now what is Mn? Mn is supremum of x belongs to 0, 1 mod of fnx minus fx, right? Which is supremum of x belongs to 0, 1. Since f is 0 here, our f function is 0, and fnx is this number, so it is basically nx by 1 plus n square x square, right? And we have seen that from this observation, this, so what we found that this number is less equals to half, and equality holds for x equals to 1 by n. Now x equals to 1 by n lies in between 0 to 1, right? So equality will hold in this 0 to 1. Since here our 0, 1 and 1 by n lies in this 0 to 1. So supremum will attain, and supremum value is what? Supremum value is half, right? So this means Mn does not go to 0 as n tends to infinity, because Mn is half, always half. So it is not going to 0. So by this theorem, if Mn does not go to 0, then it will not be uniformly convergent. So this means Fn converges to a pointwise, but not, so Fn, this sequence Fn does not converge to f uniformly. Right? Okay, so let's see another example. So here our fnx is defined by x square e to the power minus nx, where x belongs to 0 to infinity. Now show that Fn is uniformly convergent on closed 0, 1, not on the whole domain, but in this closed interval it is uniformly convergent. Now first we have to find out the pointwise limit. So I think we have already done this. Or limit n tends to infinity, fnx is what? It is x square by e to the power nx, right? So when n tends to infinity, for each x, each fixed x, it is going to be 0, right? For all x belongs to 0 infinity. Right? Or it is actually given 0 to 1. So for each, all x belongs to 0, 1, the pointwise limit is 0. So if x equals to 0, the 0 function is the limit, is the pointwise limit of the sequence fn, right? So fn converges to the 0 function pointwise. Now we'll prove that it is also uniformly convergent. So for uniformly convergent, we have to check this Mn, which is supremum of x belongs to 0, 1 mod of fnx minus fx, right? Now since f is 0, so it is supremum of fnx is x square to the power minus nx, which is a positive number, so it is x square to the power minus nx, right? Now we have to find the this Mn. So take ux to be this number, this function x square e to the power minus nx in 0 to 1, right? Now you have to find the supremum of this, supremum or maximum, since this is a continuous function and the domain is a closed interval, closed bounded interval. The supremum means it is its maximum and it will attain, right? So for maximum, what we do? We do the derivative, take the derivative and take the derivative to be 0, and that gives the critical points, right? So u dash x is plus or minus which is x e to the power minus nx into 2 minus nx, right? So now if we take u dash x to be 0, then what we have? We'll have, since x is arbitrary, x is varying, so this means 2 minus nx is 0, right? So this means x to be 1 by 2n. At the point 0 is also, it is 0, right? This is 0 or x equals to 0 and x equals to 2n. So these two are the critical points of ux, right? So at this point they may attain maximum or minimum points. Now we see that u dash x is greater than 0 if 0 less than x less than 2n, right? From here, because here 2 minus nx is greater than 0, so u dash is greater than 0 when x lies between 0 to 2 by n, and it is less than 0 if x is greater than 2 by n, right? And equal to 0 when x is 2 by n. So we see that if here is our 0, 1 and here is some 2n, then u dash greater than 0 means it is increasing from 0 to 2n. At 2n it is 0, may not be a straight line. At 2n it is 0, and then again it will decrease to 1. Right? Now at x equals to 0 it is 0. Right? So at the point x equals to 0 it is taking its minimum value. Right? Because ux is 0 at the point x equals to 0. And before 2 by n it is increasing, and after 2 by n it is decreasing. So this means 2 by n is a maximum point. Right? So this means x equals to 2n. So un attains its maximum. So ux attains its maximum at x equals to 2 by n. Right? And we are finding the supremum of this, maximum of this ux. So mn is what? Mn is actually u 2 by n. Right? Because at 2 by n it is attending is maximum value. So it is 4 by n square e to the power minus 2. Right? So it is actually 4 by e square n square. Right? This is the value of mn. Now it is clearly tends to 0 as n tends to infinity. Right? So this implies Fn converges to F uniformly. So Fn converges to F uniformly on 0 to 1. Right? Now instead of 0 1, if we take 0 infinity, this will also be true. Right? Because the maximum point here, the 2 by n, lies between 0 to 1. So if we take 0 to infinity, this function is also Fn converges to F uniformly also on 0 to infinity. Right? Okay. Now let T is a subset of R, and for each n belongs to n, Fn, which is defined from D to R, is continuous on D. Right? And let Fn converges to F pointwise. Okay? Now, since each Fn is continuous, can we conclude that F is also continuous? The question is F continuous on D? The answer is no, because we have already seen this example fx equals to x to the power n when x belongs to 0 to 1. Here Fn converges pointwise to a function fx which is 0 when x belongs to 0 to open 1 and 1 when x equals to 1. Right? So this function is not continuous. So it has discontinuity at the point x equals to 1. where f is not continuous, right? So pointwise convergence does not imply the continuity of the limit function when all this fn is continuous, right? But in case of the uniform convergence, we can say that when fn converges to f uniformly and each f is continuous, then the limit function f will also be continuous. So this is a theorem. So I am just stating this theorem. I am not going to the proof. You can check any book for this proof. Okay. So let D subset of R, and for each n belongs to n, fn from D to R is continuous on D. Now if the sequence fn converges to f uniformly, or we can write this as if the sequence fn converges uniformly to a function f, then the limit function f is continuous on D. Okay. So uniform convergence will imply the continuity of the limit function if all the fn's are continuous, right? So in this problem solving session, we have discussed about pointwise convergence and uniform convergence of sequence of functions, right? So okay, we'll end this session here. Thank you.